Okay, welcome to this video for Chem 161, looking at some Chapter 5 materials, looking at some practice for polarity. Okay, so we've previously tackled questions on how to determine the molecular geometry for molecules based on the name. And so that's going to be a key activity in doing these examples. But we'll push ourselves and determine the polarity of the molecule as a final step. So we'll go fast on determining the molecular geometry. But if that was too fast for you, please rewind and visit the Vesper practice video that we have on determining molecular polarity. Okay, so first thing to do is get the name correct and determine the formula. So carbon tetrahydride, we're handling here CH4, also known as methane. Lewis structure here is going to be based on 8 valence electrons. And so just by building the skeleton, you're going to complete the correct Lewis structure. And that's what we've got. So we identify here that we've definitely got a steric number of 4 bonded atoms, no lone pairs at the carbon. And therefore our electron group geometry is tetrahedral. And noting that there are no lone pairs without carbon, the molecular geometry is also tetrahedral. And we can now consider drawing the molecule to reflect the actual three-dimensional shape. Carbon, hydrogen atop, 109 degrees to the next one. Send one hydrogen back and bring one hydrogen out of the plane of the video here. And there's our tetrahedron. Looks like a 4-point jack, 109.5 degrees, perfectly between each of those bonded hydrogen atoms. We now apply bond dipoles. So we note that the electronegativity value of hydrogen is 2.1, that of carbon is 2.5. And so even though there is a small dipole, and we would normally regard the individual bonds as being nonpolar because they're at a value that's at our limit of kind of 0.4, and we know that these would sum up to a net, could sum up to a net difference. So we will draw them, is the point of that. So here are the bond dipoles towards the more electronegative carbon. We note that they're equal in magnitude to one another because each is a CH bond, and that they're spread around the three-dimensional space evenly, taking the form of a perfect tetrahedron. So every angle is 109.5 degrees, and that allows these to cancel out perfectly. So we're going to see that there is no net vector to describe the overall molecular dipole. So there's no molecular dipole, no net molecular dipole here. And so we will call this molecule nonpolar. Okay, looking at the next example, nitrogen trifluoride, dealing with NF3. So 5 plus 21, 26 valence electrons. So the Lewis structure for this one would be the following. And again, going really quick here just to focus on the new content. If this is too fast for you, please rewind to Lewis structure videos for this. We now identify the steric numbers. So there's a lone pair, 1 and 3 bonded fluorines. So this is a steric number of 4 as well. We are dealing with, therefore, a tetrahedral electron group geometry. Ignoring the lone pair, we can describe the structure after drawing this. So we'll put a nitrogen here, put that lone pair atop, send one fluorine over here, send another fluorine to the back, and a wedge fluorine coming out of the page. So this looks like a pyramid with nitrogen at the apex. So we'll call this a 3-point pyramid, a trigonal pyramidal molecular geometry. Can now comment on dipoles. So fluorine's the most electronegative element in the periodic table. So I'm expecting each of these bond dipoles to point towards the fluorine. And with threefold of those pulling on the bottom of the molecule with a small amount of delta minus due to the lone pair, we can deduce that the overall fluorine is going to outweigh the effect of the lone pair, and we can draw a net vector here, which would be pushing right through the middle of the molecule, pointing straight down through the center of the three-point base of this pyramid. So there is a net vector here. So a net dipole is the result here. And so this is a polar molecule. Okay, moving on, carbon dioxide, CO2. So here we're dealing with 6 times 2, 12 plus 4, 16 valence electrons for the structure, carbon, oxygen, oxygen, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay, so there we've used 8 and 8. In order to complete the octet at the center, we have to do double bonding at each oxygen to get our correct Lewis structure. And we end up with this as our answer. So looking at the central carbon, we have only 2 electron groups. That is a twofold bonded oxygen at right and left. So we're in this category here. So our steric number is 2. We are dealing with the linear electron group geometry there. No lone pairs on that central carbon. So our answer is also linear for the molecular geometry. So just drawing that again, we would only maybe draw just these and exclude the lone pairs. And that would be our valence shell electron pair molecular geometry in line with the description of a linear structure. We can now consider bond dipoles. Oxygen is more electronegative than carbon, and so we would draw bond dipole like this, and one in equal and opposite direction the other way around. And so this is like 2 twins pulling perfectly on either arm of your arm. If they're equal in strength, they're not going to be able to displace you because they're equally strong at pulling you, just in opposite directions. So the overall is cancellation of these 2 bond dipoles because of their opposite direction. And so there's no net molecular dipole here. Nothing to draw as the sum. And so this is non-polar. Good. Oxygen. So as we saw in an earlier video, oxygen was this. Because we don't have a central atom, the steric number is a non-applicable question. We are dealing with a linear molecule, therefore. And so, in short, to focus now on dipole, because these are equal and opposite on either side of the central point of the double bond, we would expect no reason to draw a net dipole. So this is also going to be, as a result, have no net molecular dipole, and therefore this is nonpolar. Okay, sulfur dioxide, SO2 is the formula. We've got 18 valence electrons to work with. And if you recall the structure on this one, it first started with an incomplete octet at the central sulfur, and we knew we had to establish a double bond either at left or at right, so we were going to handle a Lewis structure that needed to be described through resonance. So the correct answer for the Lewis structure is going to involve two structures. As such, so that is the correct Lewis structure with resonance to describe the answer here for sulfur dioxide. You can see that we are dealing with 3 electron groups at sulfur, lone pair, and then the 2 oxygens. So this is in that middle category, so we are dealing with electron group geometry of trigonal planar. If we ignore the lone pair and then think about what this molecule must look like, it's going to look like this in resonance with the 2 options. And therefore, those are all going to lie in the plane, and so you can see that the molecule appears bent. And we can now consider bond dipoles. So oxygen is more electronegative than sulfur. It's higher in the periodic table. They're both in the same column, column 6. So we would expect to draw bond dipoles as such. Because the bond order of the double bond is more like 1.5 and the bond order of the single is more like 1.5, we know that the scenario for the opposite or partner resonant Lewis structure is also going to have the same kind of ideas there for those bond dipoles. Should be equal and opposite in equal in magnitude but opposite in direction, and so they would sum down the middle of the structure. And so we are going to predict a net result here. So there will be a net dipole going right through the molecule, pointing downward as the sort of downward directions of both vectors add together, but the left and the right components of each of those vectors cancel out. Okay, so the result here is, yes, we have a net molecular dipole, and therefore this is a polar molecule. Okay, lastly, arsenic trichloride, AsCl3, and so we could put the arsenic at middle. We know that this is going to be based on 26 valence electrons. And we'll end up with Lewis structure like this. Okay, so again, we've identified steric number 4, considering the lone pair and the 3 bonded fluorine atoms. So this is tetrahedral in electron group geometry. However, when we consider Vesper and draw this with 3-dimensionality, we're going to put that lone pair up, one of the fluorines there, send 1 fluorine back, and bring 1 out of the page. And so similar to what we saw in nitrogen trifluoride, we are dealing here with a trigonal pyramidal molecular geometry. And we can consider the dipoles now, with fluorine being the more electronegative element. We can expect those to be driving towards the fluorine. In each case, that should outweigh the contribution of a single lone pair atop, and we can draw the net result here of a bond molecular dipole going all the way through the molecule, crossing through the 3-point base of this pyramid. And so yes, there's a net dipole, of course. I've just drawn it. So this is a polar molecule as well. Okay, so there's some examples. gone all the way from the name through the Lewis structure, determined bond dipoles based on electronegativity values, and summed those up with a sort of vectorial approach respecting both quantity and direction, determining a molecular dipole, and ultimately answering whether or not the molecule would be expected to be polar or nonpolar based on whether or not that molecular dipole